Thank you very much, Orazio. It's really a pleasure to have been invited to this kind of Woodstock of the laser. I was not expecting to see so many people, and especially young people. That's why I say Woodstock. Yeah, that's good. Thanks again, and really, also I'm really pleased to help to contribute to this really 150th anniversary of this Politecnico di Milano, who really did a lot. You know, you have seen the contributions through Orazio's talk, but also the number of students who have been sent abroad, and we have all benefited from them. And a fantastic student and great training from this school, this Orazio school. Okay, so I'm going to talk about, we are going to change gear a little bit, so I'm going to talk about extreme lights, which is come naturally from the shortness of the pulses, you know, as you have seen them. And in what I'm going to, in my first slide here, you see Higgs, you know, Peter Higgs, which is kind of a symbol of high energy physics, with on the right-hand side Towns, who is really kind of the founder of this field. And now what we are talking about is trying to do change of paradigm, trying to use photons now, where maybe electrons or particles were used before. Okay. So we start this way by, you know, like Professor Svelto reminded us that at least laser is 53 over 50 years. And it was a simple thing. And now, if you look at what happened since 50 years with the laser, when the laser came, of course, the photon energy was EV. Okay? And it moved in two directions, basically. In one direction, we use these photons, these EV photons, to slow down atoms. And basically to go to characteristic energy in you know, in a microelectron volt, and now we are in kind of a almost picoelectron volt. Anyway, and that's the field of atomic and molecular optics. This is the field of quantum optics, and so on. Now, the interesting thing also, the laser moves, you know, in other directions. That is, we use the laser to accelerate particles. And now we can really accelerate particles to GeV. And it's very clear that we will be to accelerate them to certainly the TeV, and maybe, and this is what we are working on, maybe the PeV, okay? A PeV is 1,000 times CERN, okay? So that's just to give you a scale. And you can dream about because of the laser. So first of all, just, you know, if I'm looking at these two, in these directions here, people try really to make the laser very quiet and trying to produce the longest waveform possible, the highest number of cycles possible. You know that now we can produce, we have the frequencies defined at 10⁻16 or so, okay, which means 10⁻16 means that the length of the train of the oscillations basically goes from the Earth to the Moon and beyond without any interruptions, any phase jump. On the other hand, we moved in the other directions where these times, instead to have 10 to the 16 cycles, we have only few cycles. This is where we are. This is what this house is respected for, and so on. The generation only few cycles. Anyway, so until basically now, laser was involved with atomic physics. EV physics. And now the challenge is we would like to take the laser into the subatomic world. And that's not easy. And by the way, I just wanted also to really say thanks to Professor Svelto for all the things he did since 50 years, okay? And you have all his contributions here, you know, that we are using today, okay, to make very short pulses and so on. You know, he talked about the work on the cavity. He talked about the cell phase modulations. He talked about invention of the hollow fibers, compressors, generation of attosecond pulses. So I think we should really thank you very much for that, Orazio. Okay, I'm going to move now, jump back, because that was done already. And because we have to, for the type of thing that we want to do, we have to produce extremely high intensity pulses, okay? Extremely high peak power pulses. And to do that, there's a very simple formula. If you take a certain amount of energy, if you can really pack this energy in a very short times, you have power equal energy over time, then you are going, of course, to get extremely high peak power. So, and this is what we are trying to do. We are trying to do that. Except that Mother Nature doesn't let you do that easily, okay? Because when you want really to put all this energy in the laser, in a single pulse, then after that the laser cannot propagate because you are faced with nonlinear effect and so on. So in order to circumvent this problem, what we did is, so we produced these short pulses, you know, the way Professor Svelto told us, so we can get femtosecond pulses and so on. Now we have these problems, how to amplify it. And we know that we cannot just amplify it directly like that because we are going to damage the materials because, and so on. So what we do, and this is called this chair pulse amplification, what we do, we first, this short pulse has a lot of frequency components because it's short, the Fourier transform is very wide, and so we can really now, if we take two gratings, we can stretch the pulse. And we can stretch it by a large amount, 100,000 times and so on. Then we can really now, with this stretch pulse, now it's very, very long. You know, it's long, it's 100,000 times longer. So we can amplify it 100,000 times better, okay? And then now, what is amplified, you have to do just the converse. We have to put all the frequency back, okay? And together in order to get the short pulse again, okay? And so with this was a tremendous help to get into really now the high intensity regime. And that's the reason now we can talk about what we do. So until now, basic science, basic physics, I should say, high energy physics, was done, of course, with particles, because it was the age of the electrons, you know, the 20th century. Now, like Professor Svelto says, we are moving into the age of the photons, and maybe high energy physics is going to do the same. So this is what we try to do. So now, this is what I want to say. Now, the 21st century could be the photon century, and fundamental research can be driven now by this massless and chargeless particle, the photons. Okay. So, so this is really basically displayed the power or the intensity of the laser that we could obtain on target, you know, since the beginning, okay? Since 1960, we had a very quick increase because of the Q switching, because of the mode locking, and so on. And then we stop at 10 to the 15 watt per square centimeters. This is where we were stuck with nonlinear effect, and for 20 years we had to stay at this level. And then with the CPA, we were able now really to climb this slope, okay? And now we are, and of course when you increase the intensity, you are discovering new law. You are discovering things that, things changes, For instance, this is, at 10 to the 18, for instance, there's something very significant happening, is the fact that the electrons, and you have electrons, everywhere, of course, and the electrons in the field of laser now, over very short times, over femtosecond, over the period of the light, becomes relativist. The mass of the electron changes, okay? So you don't expect things, so things are going to change. And you will see that change a lot, in fact. So as we climb here, and we come to a regime where 10 to the 14, 10 to the 15, it's not only the electrons which are becoming relativist, but now the protons and all the ions, for that matter, are becoming relativist. So things are changing. And then if you go even higher, then if you interact with vacuum, you are from the light, you are producing matter, okay? Vacuum is turned into matter, okay? You materialize light, okay? And this is, this is where we are today at 10 to the 22, but we have new installations, which is the ILE and ELI. I don't have the time to talk about it, but where we will have relativistic protons, and then we need to go to materialize light. We need to go higher. And we had Federico. I don't know if Federico left, but he's always telling me, so Gerard, when are we going to really break down vacuum? Okay, this is another way to say materialize light. But it takes, of course, very, very large systems. Okay, this is basically the type of the systems that we need in order to do physics at these different levels. Okay, so now there's one thing very important, as I said. At one point, at 10 to the 18 or so, we are getting into the relativistic regime. Okay, so if you are taking an electrons, in the field of the laser, the electron moves up and down roughly. Okay, so it's perpendicular, motion perpendicular to the k vector, propagation vector, and so the force, the Lorentz force, which is applied to the electrons, is this way. And normally, the velocity of the electrons is extremely small compared to the c, okay, to the velocity of light. So this term here is absolutely negligible all the time. That's why in optics, you never worry about B, You always worry about E, okay? But at 10 to the 18, of course, things change. You have to worry because the electrons becomes relativistic. So these terms becomes as important as electric terms. So now the curious thing is that instead of moving like this, if the propagation vector goes like this, it moves along now the propagation directions, because you have a V, V cross B, okay? And so V cross B gives you a term which is parallel to the propagation directions. And this is relativistic optics. This is a new type of optics, okay? Which, of course, happened because we were able to amplify. Now, if I'm focusing my beam into a plasma, A plasma, of course, is really made of electrons and ions, okay? So my V cross B is going to push the electrons in these directions. So the electrons will be here, the ion will stay behind, so you are going to build up a charge. And so you are going to produce an electrostatic field along the directions of the propagations. So you do two things. With a very high frequency light, which is transverse. In fact, what you do, you are making a static field, okay, along the propagation directions, which is ideal, of course, for accelerations, okay? And this is a very, very important property. So you will see that there's things that we can do. So here, the inventor, because that was predicted before, was Toshi Tajima, okay, in 1970, but he had to wait that the high-intensity laser, of course, happened, okay? And this is really Toshi Tajima surfing, well, almost. You see, here you have a surfer, okay? And so, and you can imagine that you had a boat. You know, this boat has produced, okay, this big wave, okay, because it's a wake field, okay? So the light going into this plasma is producing this kind of wave, a huge plasma wave. Well, now the electrons are going to really be trapped and be accelerated. And the acceleration is enormous, okay? Because as I say, what we did, we flip the electric field, transverse electric field, from transverse to longitudinal, and the laser, the field of the laser is huge, okay? And just to give you a sense, okay, this is the synchrotron SRF 3 GeV at Grenoble, okay? And this GeV has been produced from this kind of plasma capillaries. You see GeV, so you see over centimeters. And this thing is about 1 kilometer in circumference, okay? So it's enormous. Okay, now, there is problems with that, and I will tell you in a minute. But one guy, which is the director general of KEK, he said, well, we were talking to him, he said, Gérard and Toshi, try to do with your laser what we cannot do, okay, with conventional technology. Because we have a problem. We have a very low rep rate. You know, for high energy physics, people, I mean, they demand something like 10 kilohertz and things like this. And we do, you know, 1 hertz at most, okay? So, but he say, okay, that's okay. But try to do things that we cannot do. For instance, if you could try to do PEV, you know, could you do PEV? So I'll say, okay, we'll say, okay, fine. You know, PEV, if you want to produce a PEV laser with conventional technology, the size of the laser, remember CERN, the HC is 7 TeV, okay? So if you want to go into PEV regime, basically it's 100 times, 1,000 times CERN size. So it's 27 kilometers. So 27 times 1,000 is 27,000 kilometers is around the Earth. But but if you have a very large laser, you know, you could do PEV over kilometers, which is much better than 40,000 kilometers. So that was very exciting, and so with Toshi, we went and decided, we went to the some people, and basically in France, okay, the two directors of the Commission of Energy Atomique is Daniel Ververde, and of Saclay, the civilian branch is Gabriele Fioni, and we asked them, you know, if you know, we could do this type of science and so on, and they were delighted, you know, say, yeah, go ahead. So they really were very, very supportive. We went also to the States, where we met this guy. This fellow is a director of NIF, okay? So these systems are megajoule systems, okay? And NIF is, of course, a megajoule, and is working. This one is going to work in 4 or 5 years. But this one is working. It's working extremely well, by the way. I mean, the experiment is not working very well, but the laser is working very, very well. So now the idea is to take some beams and excite a plasma wave in order to get these extra very, very high energy particles. Okay? Now, what can you do with these very, very high energy particles? Well, I mean, you could go, what people say, go beyond the standard model. Okay, now I think the standard model is fairly well understood, especially because the Higgs has been discovered with 10 minus, with 99.9999 certainty. So, but now what's beyond this? So we need higher energy particles. Astrophysics also, you know, there's a lot of particles coming which are produced in a way that we are not absolutely sure, and so on. It would be very nice if we had a way to produce it, you know, on the Earth, so we could study them as opposed to stand and trying to observe them, which is very difficult. Trying to understand the vacuum. The vacuum, which is in fact is not vacuum, as you know, or maybe not, but I can tell you, it's not vacuum. Okay, it's full of activity. Okay, and we don't know much about it. So with light, we will actually now to do physics of vacuum. People are doing that now with particles, but with light. Dark energy, dark matter, measuring Lorentz invariance. Now, also doing precision metrology. We'll give you some maybe example about this. Oh, that's also a graph that I like very much. That's a piece of work that we did with Tajima, which basically says, if you want to make things short, first make it very powerful. That is, if you want to have very short pulses, you have to first make it very intense. It's kind of the converse of saying, if you want to have very high power, you have to have the pulse extremely short. But what this conjecture says, the converse is true. If you want to have a very, very short pulse, you need first to get the light intense. Okay? And we check that with everything since a free-running laser up to what we can imagine in terms of interactions, you know, and so on. Basically, it goes on a straight line. So as you increase the intensity, we are bound to observe shorter and shorter pulses. So I believe that we are not going to stop at attosecond, but we are going to see after attozeptosecond and yoctosecond, okay? As we increase intensity. So anyway, but if you have this from these systems, which are where we use these very large scale lasers, you know, we should be able to produce extremely high peak power. And one of the applications, of course, will be to produce extremely gamma rays, very, very short gamma rays, okay, could be produced. And then we could simulate some of the observations that is done. I've lost of the time. When in
after 35, 40 minutes after 35. It's about 10 minutes.
10, okay, so I have to move fast. So anyway, we could simulate on Earth what's happening in the cosmos, okay? Now, what's very exciting also, it is all the applications, not only scientific, but also societal application, because after all, it would be nice if we could do societal applications with very high intensity lasers. So there is one thing that we can do with very high intensity lasers. As I say, we can accelerate electrons to relativistic velocity, but also if we have very high power, then we can produce very high energy particle protons, okay, relativistic protons, and very efficiently. And with so this is what's nice about this field, okay? We are all being trained in optics, okay, in EV physics, but now we can clearly, the laser will take us into these new regimes in nuclear physics, as I say, atomic physics. It will take us into nuclear physics and high energy physics. So now, we will have applications, you know, is it working? Yes, okay. You know, proton colliders. If you have protons, relativistic protons, we can make neutrinos and neutrons, neutrinos, and so on. Muons from muon colliders, and also Higgs, Higgs factory, and so on. This is predictable. And that's one very important application, of course, is trying to treat nuclear waste, okay? Trying to transmute some bad stuff into neutral stuff, okay? Transmutation is something that has been thought, but you know, it's taking it takes laser systems, very, very large scale systems to do this. And for instance, you know, if you take technetium 99, okay, which has a lifetime of 200,000 years, now if you put one more neutrons, you know, and make it a technetium 100, then its lifetime decreased to 16 seconds. So this, of course, is not always, it doesn't always go like this, but you can reduce significantly, you know, the nocivity lifetimes of materials. And so this is one nice approach, you know, to trying to contain these big problems that we have with all this nuclear waste. And so, of course, these are some of the applications of if you had very high energy relativistic protons, you can make this type of system, but you will notice that these systems are huge. They are huge, okay? And instead of, you know, I showed you that we could make relativistic protons over millimeters, not kilometers, okay? So it will be much more compact and certainly less costly. So that is what we want to do. Now, there is one problem with this, with the laser, but now kind of swept under the carpet, is the fact that, yes, we can produce these protons, or we will be able to produce these protons over millimeters instead of kilometers, okay? The problem is, once again, is first, it's low rep rate, you know, Hertz. And the second problem is, so here I show the kind of a state of the art, you know, if you want to try to make relativistic kind of protons, you know, you take this type of laser. The problem is, of course, it's extremely inefficient. Our lasers are very, very inefficient, okay? 10 minus 3, 10 minus 4, okay? So, I mean, if you really want to deal with nuclear waste, you have tons of nuclear waste. I mean, you are not going to do it this way, of course. We have to change, we have to improve the efficiency of lasers, and we have to improve the rate rate, but by 4 orders of magnitude, not a small number. So it's a huge challenge. And so what I proposed about 6 years ago, what we should do is try to do that with fibers. Why fibers? Because the fibers, we haven't talked more about fiber, but single-mode fiber have an outstanding efficiency, okay? And they can be pumped by a laser diode, which have outstanding efficiency too. So you can make outstanding efficient, plus the laser output is also absolutely outstanding. So this is what we proposed, was something like to have a huge array of fibers, and we call that ICANN for international, by the way, the International Coherent Amplification Network, okay? So right now, this project has been funded by Europe, and we have France, we have Germany, we have UK, we have CERN, you know, because we need a way, okay? It's absolutely, we need a way to have, by hook or by crook, I would say, we need a way really to have peak power, average power efficiency, okay? And this right now is a nice, that is the best thing that we can do. And so we have to have millions or 100,000 fibers firing in phase, you know, and trying to produce this. So at the beginning, people say, Gérard, you are crazy, okay? But we had some grants, some money for European, from the European EU. And now we did some experiment, not with 100,000 fiber, but with 64 just to feasibilities. And we had some outstanding results for 64 fiber now. We can phase, because that was the name of the game. We had to phase all these fibers. And we have now a way to do it over as many as 10,000 fibers. Okay, we did only 64. And for instance, just to give you an idea, you have these 64 fibers which are now incoherent. Okay, when they are incoherent, this is what you get in the far field. Okay, you get a cloud. Now, as soon as you phase this fiber, that is, you have the mean to measure and you have and to control, to adjust the phase, this is what you get, absolutely perfect spot. Now, of course, we want to extend the concept to the very, very large peak power lasers. So there is an article in Nature Photonics happening in 2 weeks for the April issue, talking about this concept. So people say, well, this is very complicated. I say, yeah, that's true. But the alternative is also very complicated. This is what the type of things you have to have in order to produce a relativistic proton right now. But this is over not maybe 600 meters, and it's very costly. So I think we can do it in optics way. And so now the way maybe to try to treat the nuclear waste will be to take these lasers, and you are producing relativistic proton by focusing your beam into a target, okay? And the proton relativistic protons now are going to be shot into a second target here, and will produce neutrons. And with these neutrons now, you are going to irradiate the spent fuel and treat the waste this way. So this is LDT, okay, laser-driven transmutator, okay, concept. The story is exciting because, as you see, okay, we are working a lot with CERN. CERN, you know, basically gave us maybe the internet, okay? So this is Tim Berners-Lee, the guy who's supposed to have given us the internet. Yeah. And now what we use, of course, the internet, you know, used the fibers, and here we have Charles Chaos. We got the Nobel Prize for the fibers. And now what is nice is basically payback time. We are going to use the fibers now to help CERN, maybe, to get their next accelerator or something. There is a lot of, there's about in this, I forgot to speak about ISES, but this International Zeta-Watt Exawatt Science and Technology. This is really my new laboratories, okay, which is called like it's a name. And we have about 30 laboratories right now, okay, throughout the world, interested, you know, to move in these directions. And it's very nice. We had numbers of meetings and on the laser ascent to high energy physics. And you see this fellow here is Peter Higgs, you know, Peter Higgs. So it's very, very, we were very honored to have him, you know, because to our meeting. So this is what we do. You know, the ascent of laser in high energy physics is not easy. That's why we are working. Is difficult. Okay. So here you have Toshitajima, you know, head, you know, pulling, and myself pushing. Okay.
Where are you?
Servinia. No, down here. Yeah. So anyway, and so I would like really to leave you with this, myself sharing a laugh with Peter Higgs, okay? Because we are really trying really to make the connections between the laser and high energy physics. Thank you very much.